What we're doing is we're looking at some AP Physics C E and M material. Specifically, we're looking at a 2016 problem, question number 1. And what we have here in this is a very large squiggly diagram with 2-point charges, Q1 and Q2. And we're told that they are fixed in place, they've been glued there somehow, on the x-axis at positions -1 meters and plus 0.5 meters respectively. So this is Q1 and then this is Q2. And charge 2 has a value of 2 nanocoulombs on the right, and the values of the electric potential, so voltages, are illustrated in the given diagram, which is drawn to scale. So that means we're going to have to use that diagram for something as we move along. And let's see, to start with, we're calculating the value of Q1. Wonderful. This will be delightful. So how can we go about doing this? Well, if we're trying to find the value of Q1, what we can do is we could recognize that voltages are scalars. So if we add the voltage from charge 1 and then the voltage from charge 2, that will have to equal the voltage of some point on this diagram. And let's see, we know, where is the origin here? This is a mess. Is this the origin? Yeah, this is the origin. We know this distance here is 1. We know that this distance is 0.5. It will probably be easiest if we sum these voltages and we set them equal to 0. We could set them to whatever we want, but set them to 0 is super helpful. So let's set them equal to this point out here at B. That's at 0 voltage on this equipotential surface, this isoline. And what we can do then is we can just find the distance away from that. So if the voltage from 1 plus the voltage of 2 equals the voltage at B, which we can say is 0, then we could do this. We know that the voltage of 1 is going to equal the negative voltage of 2. So V1 equals negative V2. And if we do this, we can use the point charge values of K Q1 over the distance equals negative K Q2 over the distance. If we set these equal like this, these K values go away. And then we just need to figure out, we're going to know that Q1 is going to equal whatever the ratio of R1 over R2 is times Q2, and that it's going to be a negative of whatever that is there. So I know Q2 is 2 nanocoulombs. Let's figure out how far away we are. Oh boy, drawn to scale. This is fun. So that's 0.5. That's 1. That's 1.5. So this has a spacing here of 1, and then this is 1.5 like that. So that's 2.5 total. So we should be able to say that this is negative 2.5 over 1 times 2 nanocoulombs, which should mean that Q1 equals negative 5 nanocoulombs. Woo! That was somewhat annoying, but really just reading a lot of this diagram, the fact that it's the scale, okay? And looking at a little ratio for that and recognizing that this is going to be the easiest one to do. We could have picked some other weird point, but that was definitely the easiest point to pick. Let's see B. At point C on the diagram, draw a vector representing the direction of the E field, the electric field, at that point. So first, let's find where C is. C is up here. And we're looking to draw the electric field. It's important to remember that the electric field is always going to be perpendicular to the equipotentials or the isolines. In this case here, it's also important to remember that because this Q is -5 nanocoulombs, the electric field lines are going to be pointing towards it. Electric field lines always go from areas from positive to negative, areas of high potential to lower potential. So our line has to be perpendicular at point C like this, but we only want it to be going into a closer to that point. So we want it to be like this. This will show that it's perpendicular and we're going towards the more negative end of things. So that's part B. And we'll just put here a C diagram for the AP reader. Calculate the approximate magnitude of the electric field strength at point D on the diagram in part C. Okay, well, point D is right here. And if this is drawn to scale, we are halfway between 20 and 24 volts, or rather -20 and -24. So how can we do this? Well, hopefully we remember that we can think about the electric field as being, and depending on how you want to think about it, you could write it in either way. For an AP Physics C world, it's important to remember that the electric field is equal to the negative of dV dx or dr. I like writing dr because it's a radial distance, but it's some distance position, okay? Some displacement vector there. If you've been taking AP2, a way that we'll sometimes write this is just that the absolute value of the electric field is equal to the difference of the voltage over the difference in position. And since we can't actually integrate this, picture, but they've put us in a very linear spot here on the picture, we're going to approximate this as linear, and we're going to use this setup here. So all we have to do is say final minus initial. And it really doesn't matter. Either way, we're going to get 4 out of that. Let's just do it as -24 minus -20 volts over, and then what's the separation distance there? That's 1, 2, right? That whole distance is 2. So this is going to be 2 times the quantity of 0.1 meter, because each of the hashes was 0.1 meter, right? Yeah, because if each hash is 0.1 meter. They're 2 apart. So all we have here is -24 plus 20 gives me a -4, and we'll take the absolute value of it because that's what we're asked for the electric field. And we're just looking for the strength. So that's going to be 4 volts over 2 times 0.1 is 0.2. And 4 over 0.2 will be like 4 divided by 1/5, or 4 times 5. And 4 times 5 is 20. And then our units there are going to be newtons per coulomb, because that is an electric field. Okay, so this is what we really want to remember here. That's very important for us. And then just remembering that's just a difference in voltage. I always like to do final minus initial. And then this is just what is the spacing of your isolines, those equipotential surfaces. Okay. Part D. The equipotential, or the isoline, labeled 0 volts, is the cross-section of a nearly spherical surface. Calculate the electric flux for this surface. Okay, so we're talking about this right here. That's a nearly spherical surface. So if that's some sort of spherical charge, when we see electric flux, we might initially be thinking Gauss's law, which means a closed path integral. But what we should just remember is that flux, and this is an electric flux in our case, that's just equal to the charge enclosed divided by epsilon naught. We don't actually have to do the closed path integral here of the flux through that surface because we're just looking for the flux. So the only thing we have to do here is, since we've recognized that the flux is just the charge enclosed divided by epsilon naught, if we look at the diagram for this isoline that goes around, we have only enclosed one charge here, Q2. So that's the only thing we have to put into our enclosed charge down here. We just have to say that, look, this is 2.0 nanocoulombs, and it's divided by epsilon naught, which I don't know if you have that off the top of your head, but it is on your equation sheet. It has a value of 8.85 times 10 to the minus 12, and kind of some weird units of coulomb squared per Newton meters squared. At that point, you just rush that through a calculator, and you wind up with the greatest number ever, 226. Because I'm the 226 guy. Put my name on the door. And our units there are just as weirdly strange. Those are Newton meters squared per coulomb. If you didn't get the 226, remember this nano up here is really like 10 to the minus 9th. And because that's a minus 9th, and this is a minus 12th, but it's in the denominator, I am expecting an answer that's in the hundreds, that has 3 digits here. So that 226 looks pretty good to me. Now in part E, we have a proton placed at point A and released from rest. So where's point A? Okay, so here's point A. And they said a proton, so it's a positive charge. Calculate the work done by the electric field on the proton as it moves from point A to point E. Where is point E? Ooh, here's point E. Okay, so we're looking for the amount of work that's done as this proton is going to be moving to the right. So what we can do here is we can look at this and say, well, work is equal to a charge and then a difference in voltage. Sometimes you might just see this equation written as QV because we're looking for a voltage difference here. But that's just kind of what's going on there. Now, a technical way to think about this is our work is being done by the electric field. And since that work is being done by the electric field on our proton, let's see, we can think at this is really a negative value because this is the field doing the work. Now, what's going to happen in a second when we put in some values here is we're going to get back a positive. So what I personally like to do is this equation written on your equation sheet has the negative in there. I like to think of this as just the field is doing the work, so I just leave the work as positive when the field does it. Okay? So here's a little note. Field does work. You're going to get a positive work value there. Okay? And the reason that this field is doing a positive work is because the electric field is always pointing from the positive to the negative. So if I were to draw an electric field line out here in like a yellow, there is an electric field line pointing to the right like that. And that's where the positive charge is going to move. The only things I need here is to recognize that this isoline is negative 4 volts, and I'm starting at the isoline of a positive 4 volts. So with that, I just need the charge of a proton, 1.6 times 10 to the minus 19 coulombs. And then I just need the final minus initial potentials. So our final is the minus 4 volts minus, and then our initial potential is the 4 volts. So I'm just going to get a, and this is where that negative comes back in. I'm going to get 1.6 times 10 to the minus 19 times negative 8 volts there. If you've been carrying this negative through the whole problem, you've got the negative here, and the negative and negative have canceled out. If you like just saying the field's doing work on the positive charge and I'm going to get a positive answer, that's where you're going to get that as well. Okay? So in the end, we're going to get 1.6 times 10 to the minus 19 times 8 volts. You could write that as some tiny number, or this is an elementary charge. So you could just write this as 8 electron volts, because it's 8 elementary charge worth right there through that amount of voltage, or through a volt. So it's elementary charge through 8 volts, however you want to think about it. That's an easier way to write it. If you would like to write it out, whatever 8 times 1.6 is, that's, well, let's see, 48, 4, 12.8 times 10 to the minus 19, something like that. You could do that as well. 8 electron volts, way easier. Now we've got to figure out what's the speed of the proton when it reaches this point. Well, luckily for us, we just calculated the work, and work is equal to the change in kinetic energy, and it was released from rest. So we can just say that the value we had before, the 1.6 times 10 to the minus 19 times 8, which I think I just worked out to be 12.8 times 10 to the minus 19 joules. That has to equal 1/2 times the mass of the proton times velocity squared. For this, you cannot write 8 electron volts. You need that answer in joules there. You need it in SI units because you need your velocity to be in SI units as well. So kind of working this out in the math, we'll multiply by 2 and then divide by the mass of the proton. So we'll see that the velocity is going to equal, it's going to be the square root of 2 times the work, the 12.8 times 10 to the minus 19, all over the mass of the proton, which is 1.6 times 10 to the minus 27 kilograms, nice SI unit. And you crush that through on your calculator. Let's see. 2 times the quantity, 12.8 times 10 to the minus 19, divided by 1.6 times 10 to the minus 27, square root. Got something about 40,000. At least that's what I got, just using the 1.6. I bet if you use the 1.67 for the mass, you'd probably get something a little bit less, but I just used 1.6, so I got 40,000 meters per second. Which, boom, we're done with that one. So let's look at F. We now have an electron being released from point B. Where's point B? Oh boy, okay. So we'll do this one in green. So this is an electron right here. And which of the following indicates the direction of the initial acceleration, if any, of the electron? Up, down, left, right, in, out, or undefined since the acceleration is 0, and justify our answer. Okay, so let's take a look at this. Well, we know that the electric field lines at point B are going to be pointing this way because they have to be perpendicular to the isoline that exists there. Because of this, I know that since that electric field does exist, there will be some force there. It cannot be up or down because this electric field is to the right. It cannot be in or out, and it cannot be undefined because the electric field is there. It has to be either left or right here. I also know that electrons, being negative, move opposite to the direction of the electric field. So this electron is going to move to the left. So for this, just by drawing that electric field, I know that the electron's going to move to the left, And then I can just state for my justification that electrons move opposite to electric field lines, and these lines run perpendicular to equipotentials. And that's it. So that one wasn't bad at all. No calculus in that problem. Just a lot of remembering potentials, understanding equipotential diagrams, understanding what flux is, a charge enclosed divided by epsilon naught, understanding work, understanding energy, and understanding diagrams again. So that was a kind of neat problem. If you haven't looked at one of these diagrams in a while, it can be confusing, but that's why we're here. That's why we're looking at it. And with that, Physics E&M from 2016, question 1 is finished. Have a good one. Take it easy.